Okay, so did you figure out what mistake we'd made here? This is what I'm talking about when I'm saying you're going through these questions. There's going to be things that come up where you think that's consistent with what I already know, and you should feel confident to add it, or you're going to come up with something like, yeah, that does not compute, or that doesn't work with what I already know about this function. That's your sign that something's gone wrong. So when I go back to look at this, what I forgot to do here is analyze that this x-intercept at -2 is actually an order 2 root, and that means I'm expecting there to be a bounce when I go to draw it. So, just to go back to what this would look like, this root is supposed to bounce off, and then I can sort of see how to finish the function from there. Okay, notice again, this like local min, or excuse me, local max in this region here, I don't really know where to draw this. Usually it's about halfway between the intercepts, but it's hard to say. Let's draw this one and we can kind of see what it's supposed to look like and can compare. Again, I'm not that interested in making sure that it's, precisely what the graph should look like. I just want to see the right shape, and I want to see the things that we've talked about correct. Anyway, what should happen here when I put this sketch is it should go through basically everything we said it would. It has to bounce off of B. It has to have end behavior here and here. Bounce off of B, go through A, and then and go down through C. And it looks like A is pretty much the local max here. That's not really always the case, but it does seem to be the case here. Okay. So there's a couple more. I think this one is pretty straightforward. There's a bounce at x equals 1. There's a bounce at x equals 2, -2. This has a parabola shape, whereas this has a quartic shape. What that means is it's going to look a little bit flatter. The end behavior for this one behavior is up for both sides, and the y-intercept is equal to, if we plug in 0, we get -1 to the power of 4 times 2 to the 2, which is 0.4. So quickly, we're just looking at, just grab this one quickly. To graph this one, we're looking at 1, 0, 0, 4, and -2, 0. I know there's going to be a parabola-like bounce off of the first point, and a quartic-like bounce off of the second point. So, something like this. So a parabola-like bounce here, and then a quartic is just the same thing, just a little flatter before it comes back up. And sorry, that's horrible, but I'm doing it with my mouse. Just to draw this one properly, x plus 2 squared, x minus 1 to the power of 4. And this will give you a better sense of what I'm trying to say. The parabola bounce can be pretty sharp. The quartic bounce is pretty flat, right? You see the difference there? Again, we're talking about a quarter point on your question to remember that this is how it works. But again, it's a quarter point you don't want to give away. So a parabola bounces off, more like a parabola does, and a quartic bounces off in that like flat quartic shape is more accurate. Okay, so again, once you get the hang of this, they're pretty quick to draw. You sort of start working on them. Here we know. Let's examine what's going on with this one. So we have a y-intercept of 0. I can tell that right off the bat because if I plug in 0, it doesn't matter what 0 minus 3 and 0 plus 1 is. 0 to the power of 6 at the beginning is also equal to 0. So this one has to pass through the origin. We know it will pass through the origin. So you can start with the point of 0, 0. Okay, so origin equals x-intercepts. We have the origin, 0, 0. This is going to be order 6, which is just going to be a very flat bounce. It's going to be just more flat than the order 4 bounce is that we looked at above. There's an x-intercept at x equals -1. This is going to have a cubic shape. It will pass through. It will not bounce, but it will have a cubic shape. Finally, there's an x-intercept at x equals 3. And this will just have a line shape, so we'll pass through cleanly. If I look at the end behavior, if I look at the overall degree of this function, let's think about it this way. It's an order 6, an order 3, and an order 1. So we add up all that together, we get 10. So it's degree 10, which is even degree, and the leading coefficient is a negative, so our end behaviors are down and down. Like, we're expecting both sides to go down. Okay, so let's take this information I've just gathered and try to map it onto our drawing. So at x equals 0, we have an x-intercept that's order 6. At x equals negative 1, we have an intercept that's a cubic, it's order 3. So negative 1, 0. And then at 3, 0, we have a line intercept. There's no need to draw a y-intercept here, and we know that the function ends down towards negative infinity and down towards negative infinity. So quickly to draw this one, the negative 1 root is a cubic shape, so I'm going to draw coming up towards this point B and then come through it like a cubic. Okay, this root here at A is a root 6, is order 6, so it's just really flat bounce, and then just straight through on C. Okay, so something like this. I mean, again, this sort of thing I've drawn in the middle is pretty exaggerated, but it's kind of what I expect to see. So if we go negative x to the 6, x plus 1 cubed, and then times x minus 3, which was this function, you can kind of see what it looks like. I drew this part way too tall, and this part not nearly tall enough. But that's the kind of thing I'm talking about, where I really don't care, what those look like. It is the correct shape. I know this looks really flat, but if we zoom in, you can see it does have the tiniest of positive regions there. So again, quite a strange one, but I don't want you to think that this whole thing is flat. It's not in this case. And again, if we weren't sure of that, we could sub in f of negative 0.5, and we get a positive number, right? We do not get 0, we get a positive number. So that's that. Again, how tall this one is? Well, it goes all the way up to 6,000. So, how would you know to draw it up to 6,000? You won't. This graph is obviously ridiculous for trying to draw up to 6,000. I'm just looking for the shape. Okay, so I would want to see, that you have the right positive negative intervals, your behavior around the roots is right, and you have the right end behavior. Okay, so come up, draw a cubic, turn around, draw a degree 6, a very flat one, go up and come back down through point C in a straight line. Okay, now let's go ahead. We might as well finish. I think we'll have just enough time to do this. So this one here, let's think about the degree. So the degree for this one is degree 1 plus 5 plus 2 plus 1, right? You see each factor. I can count the order of each factor, and that will tell me the degree of the overall function, which in this case appears to be degree 9. The leading coefficient is positive, so my end behavior is equal to low to high. Again, I do not want you to write low to high on a test. I want you to write x approaches negative infinity, y approaches negative infinity, and x approaches infinity, y approaches infinity. Just high to low or low to high is just like a common sense way of saying it, but it's not the way I want you to say it in terms of a test. So maybe we'll just get rid of that. Okay, so we know how this one's going to look. It's going to have opposite end behaviors. It's going to start in the negative quadrant. It's going to end in the positive quadrant. It's degree 9. Okay, the y-intercept for this one would be 2 times negative 1 to the power of 5, which is negative 1, times 1 squared, which is 1, times 4. So this is altogether, that's equal to negative 8. So quickly, for this one, we could go through this and draw 0, negative 8. okay, which of course I can't see at the moment, but pull it back to a reasonable view and we can see it again. Okay, let's go through and track our x-intercepts. X equals -2. Sorry, x equals -2. That's order 1. So shape passes through like a line. X equals +1. So x equals 1. This is order 5. Passes through like a cubic, just a flat, like a flat cubic. Okay. X equals -1. Order 2. Bounces like a parabola. And finally, x equals -4. Order 1, which passes through like a line. Okay, so again, I'm not going to go through the process to sketch this one. Let's just draw it and have a look at what we expect to see. So again, we have an intercept at x equals -2. We have an intercept at 1. We have an intercept at -1 and -4. Okay, we know that the one that's going to behave the strangest is the one at +1. It's at order 5. It's going to look like a really flat cubic. So let's go ahead and just take a quick look at what this one looks like. So this is to the power of, and this is to the power of. Okay, so again, it's exactly like what we thought it would look like. Its end behavior is negative to positive, right? Starts low, ends high. Okay, in the middle, again, this is another one of those ones you could never hope to draw accurately on a graph, but just looking for the right shape. So it passes through E like a line. It passes through B like a line. It bounces off D like a parabola. And it passes through C like a cubic. It's a quintic, but you know, a cubic and a quintic look the same. It's just flatter. The quintic is just flatter than the cubic. Okay, so the last thing to do here before you try the practice, and you know, there is a handout here to help you with this as well. I just really strongly recommend you do this. I believe also you have an assignment that is that you can now do. Okay, let's try this. This type is the other way I like to ask this question, which is to tell you the information and then you have to sketch the graph. So it says degree 3, positive leading coefficient, 2 zeros, 2 turning points. Okay, so let's take that over to GeoGebra and see what it is what we can do. Okay, so degree 3 with a positive leading coefficient. Let's start with that. A positive leading coefficient tells me that my end behaviors, it's odd, so my end behaviors are going to be in opposite directions. The fact that it's positive tells me that it's going to approach negative infinity as x approaches negative infinity, and positive infinity as x approaches positive infinity. So that covers the degree, it covers the leading coefficient, and I now am going to draw 2 zeros, let's say one here and one here. And now I'm going to attempt to sketch my picture. Again, I run into a problem here, which is I need another 0. Of course, I don't have the ability to create another 0. I'm only allowed to use the 2 that they told me about. I also didn't draw enough turning points here, right? So we got 2 problems that we can fix using the same solution. Okay, the solution is, much like it was earlier today, to create a bounce in one of these, either one of these options. So let's say we bounce off E. Okay, that would work. I now have 2 turning points, and everything is consistent with a degree 3 positive leading coefficient 2, 0, 2 turning point option. A good equation for this might be something like x plus 1 squared times x minus 1. Okay, and then that kind of looks like what I drew. You know, sort of. It's just kind of compressed. Oh yeah, it does stretch. Okay, so this would be one option, right? What I just drew. Another option would be to take the bounce on F instead of the bounce on E. So, you know, it might look something like this instead, where we come up through E, bounce off F, and then go through. If that's the case, your equation is simply going to be x plus 1 once and x minus 1 twice. And you can see again the function looks more or less like I predicted. Okay, so to wrap up today, you now know how to sketch a polynomial from factored form, paying special attention to the number of times a factor repeats, which is the order of that root.